After being fully charged, there is a potential difference, which we will call delta V, between the two plates. Delta V is equal to the voltage supplied by the battery. So you can see we will arbitrarily assign this as 0 and this is plus V, so delta V is V. There's a uniform electric field between the plates, and we learned earlier that with a uniform electric field, delta V equals minus E delta X, where delta X is your change in distance in this direction. This obviously will be true in the case of the parallel plate capacitor because we have a uniform electric field. The electric field is constant everywhere in the gap between the plates. We've learned that already. The electric potential, the voltage, declines uniformly from plus V to 0 within the gap. You can see plus V, 3/4 V, 1/2 V. You can see how that's a linear progression there. On a ruler, this would be 0, 1/4 inch, 1/2 inch, 3/4 inch, 1 inch. Why is that just like that? Well, because of this equation right here. The change in voltage is equal to negative the electric field times the distance you move. Negative means it gets smaller in the direction of the electric field, so you start with a plus V here, and it decreases down to 0 as you go along the electric field line. That's what that negative is for. Okay, and delta X, that's a linear function. So as you go down, let's say, we'll just make some numbers up here, 1/4 of an inch, your voltage goes down 1/4 of a volt. You go down 1/2 an inch, it goes down 1/2 a volt. So it's a linear relationship. And what are these green lines? Equipotential lines, which are always perpendicular to the electric field. So hopefully you can see how all the work we spent earlier understanding equipotential lines, the electric field is perpendicular to the equipotential lines, this equation, how it's all coming together as we describe a capacitor. Why did we show the negatively charged plate with a voltage of 0 and not some negative number? Well, actually it's somewhat arbitrary. The important fact is that the difference in voltage here, delta V, is equal to the voltage supplied by the battery. We could have labeled the voltages as shown over here. We could have started at negative V over 2 at the negative plate, negative V over 4, 0, plus V over 4, plus V over 2. We still have the linear progression, and we also have the higher voltage at the positively charged plate and at the kind of the origin of the electric field vectors. The voltage gets smaller as you follow the electric field. Probably because people like positive numbers better than negative numbers, so we showed it like this. But the other way also would have worked. One of the major purposes of a capacitor is to store energy, and it stores energy in the form of the electric field from the positive to the negative plate. We're going to derive that equation now, and we're going to derive it for the parallel plate capacitor, but it will work for any geometric configuration of a capacitor. First of all, how much work would it take to move a single electron between two initially uncharged plates? So after the electron moves, we're left with a positive charge here, a positive ion. Moving the first electron takes 0 work because in the beginning both plates were at the same voltage, they were neutral. And voltage is related to potential energy, which is then related to work. So if you have 0 voltage, 0 energy difference, you need no work to move the electron. However, once this first electron is here, if I want to move another electron, this electron is going to feel a repulsive force from the electron already there. So you need work to overcome that repulsion. That work is provided by the battery. This will provide the energy you need to move the next electron to overcome the repulsion of the first one. Then moving the third, the fourth, the fifth, all the way up to the billionth electron. There's a lot of electrons here. We're just simplifying it so we understand the concept. This battery will attract the electrons, the positive terminal here. Remember, the positive terminal is a longer horizontal line. It will move through the battery and get deposited on the other plate. The electric force is a conservative force, so the work done on this longer path here, as opposed to just going straight through here, is just the same, so we're going to use that as a model. And remember, the electrons can't move directly between the plates. You have all this air here that's insulating it and not letting the electrons go. So we have this wire connected to a battery, to another wire, to the other plate to let the electrons flow.